Hello, everyone. Today, I'm joined by my first period Algebra II class. We're a day behind because of the weather. You'll notice today's date that I'm taping this is December 16th. It's a very special day at the Minnick household. It's Mrs. Minnick's birthday. And no, I did not get her anything just yet. And she knows it. And I'm in trouble. And you are in trouble too if you don't take copious notes. Here we go. Chapter 5, Section 1, Polynomials and Polynomial Functions. I will preface this by saying, don't forget all the stuff from Chapter 4. But we just took the Chapter 4 test, and we might not have done so well. Well, go back and look over it. Because everything from Chapter 4, especially solving quadratic equations and factoring, it's assumed that you can do all that stuff. And you can do all that stuff very well. Because when we get to the second half of the chapter, you're going to need to know how to do all that stuff still. So you'll notice these bullet point things. These are all the things that we're going to get through in the next 38 minutes or so. So let's just get right to it. The definition of a polynomial function says, for any natural number n, no dot, that's my abbreviation for number, for any natural number n, and real coefficients a sub n minus 1 dot 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 a sub 2 a sub 1 a sub 0.
Take your attendance.
So for any natural number n and any real coefficients a sub n minus 1 dot dot dot, a polynomial function is defined the following way. So the first bit of information, it seems kind of scary, and wait till when you see the definition, it's going to be even more scary. All we're saying is anytime an n shows up, it's a natural number, okay? Like 1 or 2 or 3. Anytime there's coefficients, the coefficients have to be real, okay? They can be irrational, but they have to be real. So a polynomial function is defined as this. P of x equals, the P obviously stands for polynomial. The first term in a polynomial function, it's real imperative that you understand the components of it. The coefficient of the first term is a with a subscript n. That's not the preposition an, that is a with a subscript n, okay? And then there's an x next to it. And there's an exponent on that x, and that exponent is n, and we'll be talking about all these parts, okay? So a sub n times a sub n x to the n plus the second term, it has a coefficient a sub n minus 1. And the notation's kind of weird. It's just saying, well, that's the next exponent, okay? Or the next coefficient, rather. And again, we're going to have an x. And the power on x this time is going to be 1 less than it was before. And we'll explain what all that means in a minute. And we could keep on writing this pattern a sub n minus 1, x to the n minus 2, but we're not. We're going to go all the way down to the last two terms. So we're going to say that this pattern continues a while. And the last two terms are going to kind of look like this. The last two terms are going to look like this. Actually the last three terms. A sub 2 x squared plus a sub 1 x to the first, and I really don't need to write that one. And then finally in the end, plus a sub 0. So it's kind of scary, and this is the way all textbooks define this, okay? It's really weird notation, but don't let the notation scare you. It's really not as bad as it looks. It's not. So the very first term, if you would, this whole thing, a sub n x to the n, that first term has some parts to it. A sub n is the leading coefficient. A sub n is the leading coefficient. Okay. We're going to be referring to that when we start talking about n behavior, but a sub n is the leading coefficient. n is the degree. N is the degree. And to put that in layman's terms, all n is it's the largest exponent. It's the largest exponent on the variable x. On the variable x. Okay. So the n as a superscript, it's the degree of the function, and it's also just the largest exponent on the variable x. And then finally, a sub 0 is the constant term. A sub 0 is the constant term. Now, from studying lines, we looked at y equals mx plus b with lines, right? And the b is the same thing as that a sub 0. When we studied standard form quadratic functions, we saw y equals ax squared plus bx plus c. And the c was the a sub 0. What do we know about the b from lines and the c from quadratic functions? Anybody remember what part of the graph that was? It's the y-intercept. So, by the same line of reasoning, this a sub 0 is also going to be our y-intercept. Okay? So that's the way a polynomial function is defined. Later on, we're going to be talking about theorems of polynomial functions and how we can find roots of polynomials. And we're going to see that definition again. Okay? So what the big idea is to take home, the exponents are natural numbers. 5, 4, 3, 2, 1. The coefficients of the variables, the a sub n minus 1, whatever, those just have to be real numbers. And the constant term is our y-intercept. The big idea is to take home. Any questions before we move on to the next idea? If not, the next idea here is standard form. Okay? So this will be our first example. Example 1, write each polynomial function in standard form. Now, the interesting thing about standard form is it's true for all polynomials. It's universal, no matter what country you study them in. You have to write the terms. The terms must be in descending order. In descending order by degree. Descending order. In other words, the biggest exponent first, then the next biggest exponent next, and the next biggest exponent, and so on. So we're just going to look at two of these. We're going to look at p of x is 2 plus 5x minus 6x cubed plus x squared. And we'll look at number b here. We'll call this next one f of x equals 2 minus 3/8 x. So if we look at that first one, it's pretty clear that the terms are not written in descending order by degree. One thing to keep in mind that terms, some people don't understand what a term is. Terms, like this 2 is a term. 5x is also a term. 6x cubed is also a term. Technically, you could think of it as negative 6x cubed. And then x squared is also a term, and back in the day, we might have written a plus here, plus negative 6x cubed. The point is, terms are separated by addition. Terms are separated by addition. So the deal is, we need to write those terms in descending order by degree. Anybody think they got it? What do we got? It would be negative 6x to the cubed, and then what? Plus x squared, plus 5x, plus 2. There it is. That's all there is to it. What do we think? Not so bad, right? So number b here, f of x equals 2 minus 3/8 x. What's that one going to look like in standard form? F of x equals negative 3/8 x plus 2. Okay, that's it. That's all there is to it. Biggest exponent term first, next biggest exponent term next. Easy enough? Good. It's been a while since I've done one of those. I think I might have to do 2 more. So example 2 is kind of weird. example 2, determine whether each is a polynomial. Number A, number B, number C, number D. Determine whether each is a polynomial. So here I'm not even going to write polynomial functions. I'm just going to put polynomial expressions up here. And I want you to tell me if it's a polynomial or not. 2 minus the square root of x plus 5. 2 times the square root of x plus 5. 4 over x plus 6x squared minus 8x. Pi x to the 5th minus ex to the 4th plus the square root of, not the square root of 8, that doesn't even make sense. The square root of 2x cubed plus 1. So each one of these expressions has some different things about it. Some of them are polynomials and some of them are not polynomials. And in number B, I'm sorry, I messed up number B. Hopefully this doesn't mess you up too bad. Number B, that's not what I wanted. Number B, I wanted it to look a little bit different. Let me write it as, I don't even know what I want that one to be. How about square root of 2x plus 5? There we go, that's better. That's what I wanted it to be. Sorry about that. That's a neck. I just necked myself twice. Okay. So number A, is that a polynomial? I'm seeing people shaking their heads no. Maybe you don't know why, but you're right, it's not. It's not a polynomial. We could combine the 2 with the 5, right? So if we wanted to write the second standard form, we'd actually have negative the square root of x plus 7. But there's something that makes this not a polynomial. Anybody know what it is? The square root of x. The interesting thing is we haven't even had our exponent rules yet. But this square root of x right here, when you take the square root of x, do you know what power you're really raising x to? Who said half? Long distance high five. Nice job. You're raising x to the 1/2 power. That's negative x to the 1/2 power plus 7. And what we said a few minutes ago is that the exponents have to be natural numbers. And a half isn't rational. So number A is not a polynomial. Let's look at number B. What do we think about number B? Is it? So the exponent on number B, the exponent right here, that exponent's okay. That exponent's a 1. That's cool. We said the coefficients have to be real numbers. We said that the a sub n's and all that have to be real numbers, right? For real coefficients, a sub n and so on. So I guess the question is the square root of 2, is that real? Yeah, it is. So that's a polynomial, believe it or not. It's not a very nice looking polynomial, but that is a polynomial. Let's jump down to number D. Is number D a polynomial? Pi is real. X to the 5th, that's okay. Natural exponent. The number e is an irrational number, but it is real. So minus ex to the 4th plus the square root of 2. We just saw that in number B. The square root of 2 is cool. Yeah, number D is, in fact, a polynomial. So what do we think about C? It depends on what x is. So I guess the question is, what power is x being raised to right in there? What power is x being raised to there? If x were raised to the first power there, it would be in the numerator. Well, it's not raised to the first power. If x were raised to the 0 power, there wouldn't be an x there. If x is raised to the 1/2 power, you're taking its square root. We haven't had our exponent rules yet, but the deal is in that one, in number C, the x in that first term is being raised to the negative first power. Okay, did somebody say that? Nice. Good. So we really have 4x to the negative first plus 6x squared minus 8x. So the deal is because of this, this one is not a polynomial. How are we doing? So far, so good? So the interesting thing about polynomials is what their graphs look like. What their graphs look like. The graphs of polynomials, if you could imagine a rope. In class, I've got this microphone cable, and it's about 20 feet long. That microphone cable, because it's hooked up to my sound mixer, it doesn't have any breaks in it. There's no holes in it. There's no gaps in it. So polynomials, when you graph them, they're like that. They're like that. They are a continuous curve. Their graphs are a continuous curve. What continuous means is there's no discontinuities. Oh, you just used the same word, I know. But what I mean is there's no holes in the graph. Okay? There are no holes in the graph. The graph doesn't do something like this and then something like this. The graph is one line with no holes, no breaks or jumps in it. Sometimes polynomials look like this. Sometimes polynomials look like this. But the point is there are no holes, there's no breaks, there's no jumps in the graph. They are a continuous curve. How's everybody feeling? A little side note, if we were to graph something like y equals 1 over x, the graph of that particular function looks like this, more or less. Okay, that graph has holes, breaks, and jumps in it. Okay, so something interesting to note. So the next bullet point here, it's funny, last year I'm going to give a shout out to Dr. Jones. He called this nomenclature. Nomenclature. He said he's a pretty good dude, nomenclature. Anybody know what that word means? Nomenclature. A pretty good dude. Maybe we better look it up because sometimes Mr. Minnick uses words that people don't know what they mean. And maybe Mr. Minnick's just making stuff up. So if the internet cooperates, we'll look up nomenclature. And if the internet doesn't cooperate, well, then you'll have to take Mr. Minnick's word for it. Here we go, Merriam-Webster.com. Nomenclature. There we go. Name, designation. A system or set of terms or symbols, especially in particular science or discipline or art. An international system of standardized new Latin names in biology for kinds of groups and plants and animals. So all I'm telling you is we're going to be naming polynomials. Okay? They have special names, like James and Earl and Jones. Now, we will name polynomial. I can't do a James Earl Jones impression. That'd be cool if I could. So anyway, naming polynomials. Naming polynomials. Naming them. Usually, I know I said usually 3 times, but I said that for emphasis. Naming them is usually done this way. First of all, by the degree. Not just by the degree, but by name. Name by degree. And then by the number of terms. That's the traditional way of doing this. It doesn't have to be named that way. And the name polynomial, I want you to be real clear. Polynomial refers to any polynomial in the general sense. So sometimes you're going to see the word polynomial and you're going to think, well, because of the prefix poly, that means it has to have a lot of terms. No. The word polynomial sometimes just refers to any one of these that we study. And on the midterm, there's a trick question. On the midterm, there's a question that says, which of the following is a cubic polynomial? And it's kind of interesting. The only cubic polynomial has one term, so you're thinking, well, that's a monomial because it only has one term. The trick is the word polynomial can refer to any of them, regardless of how many terms it has. So they're not naming polynomials the traditional way in that question. Does that make sense? You'll see when you take the midterm. Okay. So the degree, name by degree. I guess we need to have an example. We need an example, the degree, the name by degree, and the number of terms. So we're going to have a table here. This first polynomial we're going to look at is going to be x. That's it, just x. Just x. That's it. So what's the degree of that? The degree is the exponent, the largest exponent that shows up. What is it? 1. So if we have a first degree polynomial, there is a name given to first degree polynomials. Anybody know what it is? We studied them in chapter 1 and chapter 2 and all of algebra. Starts with an L. Linear. So if the degree is 1, the polynomial is said to be linear, and because of the number of terms, it has a special name, and it's called a monomial. A monomial. A monomial. Okay. So polynomials with one term are sometimes called monomials. Let's look at something like this. 3x squared plus 5. What's the degree there? The degree there is 2. A second degree polynomial is called what we studied in chapter 4. Starts with the letter Q. Quadratic. Because there are 2 terms, it is called a binomial. A binomial. Okay. Let's look at another example. Let's look at x to the third plus x squared plus x plus 1. What's the degree on this one? The degree is simply the largest exponent that shows up. So the degree is 3. Because the degree is 3, this reminds me of that old video game from the 80s where that thing was jumping and question marks and all kind of crazy symbols flew off his head whenever he got mad. Cubert. It's actually cubic, but it reminds me of Cubert. Cubic. So this thing's got a whole bunch of terms, doesn't it? Well, hold on. How many terms does this have? This has 4 terms. Anytime there's more than 3 terms, you know what we call these things? Polynomials. Okay. Again, keep in mind, a polynomial could just have 1 term, but if something has a bunch of terms, more than 3 in fact, and we're naming it based on how many terms it has, we can't call it a binomial or a trinomial or monomial. We have to call it a polynomial. So how is 1 a polynomial? You're talking the first one, that just x? It's a polynomial by definition. But if we were naming it based on how many terms it has, it's a monomial, but we could still call it a polynomial. We don't have to name it based on how many terms there are. That's the right way to name it, but we don't have to name it that way. It's just kind of like me. You know, my name is Matthew Minnick, and if you called me dude, I might acknowledge you, even though that's probably not the right way to address me. So let's look at this next one. Suppose we had something like 2. I've got a beef with this one. Now, most of you are going to miss the degree on this. The degree is the exponent of the variable. You're saying there is no variable. Somebody said it. There's a term here. There's an x here. What power is x being raised to? Not to the first. If it was to the first, it'd be there. It's being raised to the 0 power. So the deal is the degree here is 0. Now, if the degree is 0, we do have a name for this. We already mentioned it. It starts with the letter C. It's the same thing as what a sub 0 is called. It's constant. It's a constant. It's not very exciting when you graph it. It's just a horizontal line because it only has one term. It's called a monomial, of course. Well, I've got a problem with this one. Remember what we said the exponents had to be? We said the exponents have to be natural numbers. Is 0 a natural number? No, so technically that's not even a polynomial. Arguably, we could say it's not a polynomial at all because it doesn't fit the definition. I don't understand why textbooks never make a mention of that. But anyway, nonetheless, let's move on. So we got to look at a couple more of these because we're not done with Norman Klatcher. He is a good fellow, you know. X to the 4th minus 2x to the 4th plus x squared. I love this one. It's great. What's the degree on this one? Now there is a name for this, and it's kind of confusing. It's difficult to pronounce because you have to make that guttural sound in your mouth. It's kind of a weird sound in your mouth. Kind of like trying to say a rear wheel drive. Anyway, so this one is called quartic. 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 Q-U-A-R-T-I-C. Quartic. Be real careful with this one. I will warn you that when you're naming these, you should put them in standard form prior to naming them. What I mean by that is if there are like terms ought to be combined prior to naming them based on how many terms there are. If we combined our like terms, this would be a polynomial with how many terms? Just 2. So technically this is a binomial. It looks like a trinomial, but if we were to write it in standard form, which we should first, it is a binomial. So this is a binomial. How are we feeling? Good. So we do have a few more items up for bids. The next item up for bids is a 5th degree polynomial. X to the 5th plus x to the 4th plus 1. We haven't named something with 3 terms yet. You all know what it's called if it has 3 terms, right? A trinomial. If it has 3 terms, the polynomial in question is a trinomial. If the degree is 5, which it is here, there is a name, and it reminds me of a Bob Dylan song that he probably stole from somebody like he did with most of his other songs. There's this one song that Bob Dylan wrote about some Eskimo woman. Or maybe an Eskimo man, I can't remember. I think it's about an Eskimo man. And the man's name was Quinn. When Quinn the Eskimo gets there, I'm not going to say the rest of the lyrics because it's bad and it's inappropriate. But it's Quinn. Quinn tick. You are responsible to know constant, linear, quadratic, cubic, quartic, and quintic. You must know all those terms. I know what you're thinking. You're thinking, Mr. Minnick, what happens if we have an x to the 6th? Or what happens if we have an x to the 7th? Because a lot of people want to make this x to the 6th. A lot of people want to make this one sextic. Well, I've got news for you. You can't. Because if you made that one sextic, then you would have to make this next one septic. And that would really stink. So, if the degree is anything bigger than 6, we just say it's an nth degree polynomial. Okay? If the degree is anything bigger than 5, we just say it's an nth degree polynomial. If the degree is 6, it's a 6th degree polynomial. If the degree is 11, it's an 11th degree polynomial. Anybody ever been around when they suck out the poop from septic tanks? It's a pretty you-know-what job, but somebody's got to do it. Anybody ever been around the suck truck? I watched the fireworks in Conneaut this summer, and they had to bring in the poop truck to suck out the poop. How'd you like to be the guy that has... There's 2 guys that ride in that truck. One guy that drives the truck and the other guy that hooks up the poopy pipes. Think about that the next time you wonder why you pay extra attention in school. Because the people that do better on the tests usually get to drive the truck, and the people that don't do so well on the test get to carry the poopy pipes. Anyway. What example are we on? 3? 4? Example 3. Example 3. Find the cubic polynomial. So this is kind of your midterm question here. Number A, number B, number C, number D. X squared plus 5x plus 2. 5x to the 6th minus 2x plus 7. Negative 16x cubed, 6x to the 4th minus 5x to the 3rd plus 6x plus 1. Which one of those is the cubic polynomial? The top right one. Even though it's a cubic monomial, keep in mind that the word polynomial can refer to any one of these things that we're talking about. Okay? If we were to name these all right, what's example 3a? What would we name that based on name by degree and the number of terms? What's number A called? It's a what? It's got 3 terms, number A. It's a quadratic. Somebody said it. Trinomial, right? And what about number C? It's a 6th degree what? Trinomial. And what about number D? It's a quartic, 4 terms. It's a quartic polynomial. So that multiple choice question's kind of misleading, but they're saying which one's cubic. Well, the one that's cubic is the one that has the largest exponent in it of 3. How's everybody feeling? Does nomenclature make sense? Would you agree that nomenclature is a pretty good dude? I think we should look up a Google image of nomenclature. So there was a song on this one album called Whitney Ford Sings the Blues, called The Ends. And when we look at polynomial functions, there's basically 4 things that can happen on the ends of the graphs. And this idea is called end behavior. End behavior. And it's a universally accepted thing. It's a real big idea that can help us easily pick out a graph from a lineup. Now I'm going to get out my graph paper. I don't know if this interactive graph paper is going to work here or not. We'll find out. Find out on the playback. So I'm going to clone that. We need to have a total of 4 of these. So that's probably playing in the background somewhere. Yeah, it's probably playing. And I think I just broke my computer. Par for the course. Gotta love those days. 3 weeks later, all heck starts breaking loose. All right. So the deal is when you graph these things, one of 4 things is going to happen to the graph on the ends. And this is probably going to be the last idea that we could talk about today. There's two more ideas that we need to talk about. We'll have to hit those next week. When you graph a polynomial function, we've bared witness to graphing quadratic functions in chapter 4. When you graph a quadratic function, if my computer, there you go. If you graph a quadratic function, x squared, let's say, what does the graph do on the right side and on the left side? It's heading which way? Up on both ends. Would everybody agree to that? Let's suppose we change that exponent from 2 to, let's change that exponent to 4. What's the graph doing on the left and the right sides? Still going up. What would happen if we change that exponent to maybe 6? What's the graph doing on the ends? It's still doing the same thing, right? So the deal is, anytime the degree is even, and my leading coefficient in all those was 1, right? What would happen if I made those leading coefficients negative? The graphs would be opening down, right? So the deal is, when my leading coefficient is positive and the degree is even, the graph's going to do the same thing on the ends, and it's going to be heading up on the right and up on the left. And for now, if we were in Mr. Englehart's class, he would slap us for saying this. He does not like when I say this. But we call this end behavior up, up, for now. Okay? We're going to use better terminology later on, but for now we're going to say the end behavior is called up, up. If our degree is also even, but the leading coefficient is negative, we said we would have a parabola that's opening downward, right? So what would that end behavior look like? It would be going down on the left and down on the right, and so that end behavior would be called down, down. So if you were to look at the graph of a line, let's say, the graph of a line, something like x plus 5, what's happening on the left? It's going down, and what's happening on the right? It's going up. So the deal is, if our degree is odd, and the leading coefficient is positive, we're going to have the same thing that we have with a line. The graph's going to be heading downward on the left and upward on the right. And what would we call this end behavior? Down, up, down, and up. What happens if our leading coefficient is negative, but we have an odd degree? It's going to be what I have on my shirt. I have some up dog on my shirt. It's going to be up dog.
What up dog?
Oh, not much. So do we think that we could end on a positive note and try to identify some end behaviors based on some polynomials that are given? Key things to look for. A couple side notes too. The degree. Remember, that's a term with the biggest exponent. They might not be written in standard form. That's the only term that you care about. If the degree is even, the graph's going to do the same thing on the ends. If it's odd, it's going to do the opposite things on the ends. That's a quick, easy way to memorize that. Think about it. If the degree is even, it's going to do the same thing on the ends. If the degree is odd, starts with an O, the graph's going to do opposite things on the ends. If the leading coefficient's positive, the graph's always going to be heading up on the right. Those are things you might want to jot down in your notes, big ideas that might help with this. So here's our last example of the day. Example. Determine the end behavior of each. We'll look at number A, number B, number C, number D, number E, and number F. A lot of practice on these. f of x equals 2 minus x cubed. G of x equals 1 plus 5x to the fourth. H of x equals x to the seventh. And J of x equals negative 6x cubed. K of x equals 3x plus 1. L of x equals 17 minus 4x to the 8th. So the question is, do they need to be in standard form? No. All we need to look at is the term that contains the largest exponent. So in number A, the only thing we're going to be focusing on is the whole term that has the largest exponent. So are we going to look at the 2 or the negative x cubed? We're looking at the negative x cubed in this one. So let's think about this. The leading coefficient's negative. Is the graph going to be going up or down on the right? On the right, the graph's going to be going downward. Because the degree is 3, which is odd, what's the graph going to be doing on the other side? The same thing or the opposite thing? The opposite thing. So the end behavior then would be up, down. Be real careful how you write this. Notice I wrote what's happening on the right first. You do have to write this in the correct order. The first thing that you write is what's happening on the left. I mean, the thing on the left is what's happening on the left, and the thing on the right is what's happening on the right. Does that make sense? A lot of people kind of confuse that. So let's look at the next one. The next one, what are we looking at in number B? Which term? 5x to the fourth. Leading coefficient's positive. What's the graph going to be doing on the right? It's going to be heading up. What's the graph going to be doing on the left? Also up, because the degree is even, right? Let's look at number C. There's only one term to look at. What's happening on the right? On the right, the graph's heading up because the leading coefficient's positive. What's going to happen on the left? The graph's going down. So where do I write down? Can I write down over here? No, I got to write the down over here. Does that make sense? Okay. Anybody think they got number D figured out? What do we got? D is not down, down. What do we think? It's up. It's what I got on my shirt. It's up, dog. Nice job. Good. What do we think about number K? I'm sorry, number E. Why is D up, down? Well, we're looking at the negative 6x cubed. The leading coefficient being negative tells us that the graph's going to be going down on the right. Okay. It's been real. It's been fun. I hope it's been educational. Real quick, the last of these are down, up, and down, down. Have the best weekend of your lives. See ya Monday.